In the last lecture, we discussed how to find the internal forces of a beam given its load at a particular point. You take the beam and all of its loading, cut it at that point, and then use sum of forces, sum of moments to find the internal forces and moments. This is useful if you're worried about a beam or structure element breaking at a particular point. However, if you're not sure where the break will occur, or if you're looking for some other effect of internal stress, such as beam deflection, which you will see in later classes, you will need to find the internal forces not at any given point, but at all the points along the bridge, or along the member. Now, you could solve this by breaking the member into 1,000 pieces and calculating the internal moments in each of those pieces. I would not recommend this. We can use calculus, though, to do this and basically do it the same way. Break it up into millions of little pieces, but in a way that does not require millions of little calculations. So consider, what would happen if we took a beam and made two cuts that were very close to each other? See figure 713 in your text, or this picture right here. Well, on the cuts, we see we have shear and moment on the left side, shear and moment on the right side, and potentially some other applied force and potentially some other applied moment. So let's talk about some possible cases. First case, what if there is an applied force at somewhere on here? Now, if we think of this as a section of the beam, we need to know exactly where the moment is, or where the force is. However, because we're dealing with very, very, very thin forces, any force we find will not be sufficient to cause a change in the moment between the left and right section, so we can shuffle it off later. If we look at this in terms of Newton's second law, we see that shear on the left side plus the applied force, with the sign convention upward being positive, minus shear on the right side should be equal to 0. To put it another way, if you have an applied force right here, add that applied force to the shear from the left, and that is the shear on the right. When looking at it functionally, it appears as a discontinuous jump. And see some of the example problems to see how that works. Now, if it is a load force, so one of these W functions, then we can again get into calculus and say that if we have a very, very thin segment right here, this W function is essentially constant over this very, very thin segment. W is in fact a function, it will in fact change, but we're doing integration via Riemann sum here. So this upward force, or this upward shear, plus W times delta x equals this downward shear. In other words, we can, doing this in calculus terms, V of B, which in this case is the left, minus V of A, which in this case is V of B is the right, VA is the left, is equal to the integral from A to B of W of x dx. Lastly, we can next, we can look at the moment. So let's, for now, ignore any applied. Let's just say that this is the entire situation. There's moment on the left, there's moment on the right. However, the shear also causes a couple, because again, if there is no applied force, these two shears are equal in magnitude, opposite in direction, so they create a couple. The moment of a couple is the force times the distance. The force is equal to the shear at position x, and the distance is this delta x. So again, we have an integral function. Basically, moment is the integral of shear. Now, like with shear and applied force, we can have an applied moment. However, this is where things get annoying. Because of our sign convention, if we apply a positive moment, and in this diagram, this is the direction of a positive moment, but if we apply a positive moment to this point, that actually decreases the moment value along the beam. Please see me working through some of these problems for more details.